This video is for Chemistry in the Earth System, Unit 1.5, Tectonic Plate Interactions. Today's essential question is, how have plate tectonics influenced evolution, ocean currents, and global climate? Hello, baby birds! Today we're going to explore how the movement of Earth's tectonic plates has not only built mountains and formed oceans, but also profoundly influenced climate, evolution, and life on our planet. The slow drift of plates beneath our feet connects every one of Earth's subsystems. The lithosphere, which is the solid Earth, the hydrosphere, which is our oceans and water, the atmosphere, which is the air and our weather, the cryosphere, which is snow and ice, and the biosphere, which is life. To ground our learning, we're going to talk about the uplift of the Isthmus of Panama, which is a narrow strip of land that rose from the sea about 5 million years ago. This connected North and South America. Though small in size, this geological event reshaped ocean circulation, transformed climate, and changed the evolutionary course of countless species. Before the uplift, warm tropical water flowed freely between the Atlantic and Pacific Oceans. This equalized global temperatures. But when the isthmus formed, it blocked that flow, forcing ocean currents to reroute. Because of this, the Atlantic Ocean became saltier and therefore denser, while the Pacific Ocean grew relatively fresher. This change strengthened the Gulf Stream, which carried more heat toward northern latitudes, and this increased snowfall and helped set the stage for glacial periods. The Panama uplift shows us that plate tectonics don't act in isolation. They operate as the engine that drives global change. Every motion of Earth's plates ripples through the planet's interconnected systems. As plates move, they do far more than shape coastlines. They reshape life itself. Plate motion drives the continental drift that isolates or reconnects populations, and this influences evolution through the mechanisms of mutation, natural selection, and genetic drift. When continents drift apart, species become isolated on separate land masses, where they adapt to their unique environments. When continents move back together, species can migrate, compete, and sometimes merge evolutionary lineages. So let's connect this back to Panama. Before the isthmus rose, the Americas were isolated land masses. South America's animals, like armadillos, anteaters, and opossums, had evolved independently, cut off from their northern relatives. When the land bridge formed, these species were suddenly able to migrate north, while northern species like bears, horses, and saber-toothed cats moved south. This event is known as the Great American Biotic Interchange, and it represents one of the most profound evolutionary reshufflings in Earth's recent history. Fossil records show dramatic changes in species distribution following the formation of the isthmus. Many South American mammals went extinct while new species adapted to the new competitive pressures. In the terms used by our textbook, evolution is most pronounced when continental movement changes climate patterns. This forces organisms to adapt to new conditions. The Panama uplift did exactly that, rearranging habitats, redirecting species, and redefining the biosphere. But long before Panama, another great tectonic episode set the stage for our modern world: the rise and fall of Pangaea. About 600 million years ago, Pangaea formed as a massive supercontinent covering much of Earth's surface. And for about 400 million years, it remained a single, unified landmass. Then, somewhere around 180 million years ago, it began to break apart, fragmenting into pieces that drifted to their current positions. The breakup of Pangaea had enormous consequences for life. Organisms that had once shared a single habitat became isolated on drifting continents, And over time, these isolated populations diverged into distinct species. We can highlight examples, such as flightless birds, ostriches in Africa, as well as emus in Australia, and the tinamous in South America. They're all descendants of a shared ancestor that once roamed across Pangaea. While Pangaea's breakup promoted biodiversity through isolation, the Panama uplift, millions of years later, had the opposite effect. It reconnected previously separated land masses, triggering migrations and new ecological interactions. Both events show how tectonics act like the ultimate regulator of evolution, sometimes separating life, sometimes bringing it back together. But remember, each shift in plate position influences not just geography, but the climate zones and habitats available for life to thrive. Now, let's focus on the hydrosphere, Earth's oceans, and how tectonics can transform their behavior. When plates move, they can open or close ocean gateways, profoundly altering global ocean circulation. Ocean currents redistribute heat, fresh water, as well as nutrients, acting like Earth's climate control system. The Isthmus of Panama is a textbook example. Before it formed, warm, salty water flowed freely between the Atlantic and Pacific Oceans. When tectonic uplift closed that seaway, that flow stopped. This seemingly small change intensified the Gulf Stream, which began carrying more warm water from the tropics northward into the Atlantic. The result was a redistribution of heat across the globe, cooling the Pacific, and then salting and warming the Atlantic, and then promoting increased snowfall in polar regions. Scientists believe this circulation change helped trigger the Pleistocene glaciations, which is a series of ice ages that shaped Earth's most recent geological history. This illustrates a crucial point from our tech book. Plate motion in the lithosphere directly influences climate regulation in the hydrosphere and atmosphere. Ocean circulation patterns determine where heat is stored and where it's released. When the geometry of the ocean basins changes, the entire climate system must then readjust. Next, let's compare Panama's closing of a seaway with an earlier opening, the creation of the Drake Passage. About 39 million years ago, give or take, tectonic movement separated South America from Antarctica, forming a deep waterway between them. This opening allowed cold seawater to circulate freely around Antarctica, creating the Antarctic Circumpolar Current. This new current isolated Antarctica from the warmer oceans, preventing heat from reaching the continent and leading to the formation of the Antarctic ice sheet. Some call events like this tectonic gateways, because they act like valves in the ocean systems, either opening to allow flow or closing to restrict it. Each gateway can alter climate globally by changing how oceans move heat. Now, notice the pattern. The opening of the Drake Passage cooled Antarctica, while the closing of the Panama Seaway also led to global cooling, but through opposite mechanisms. One allowed cold isolation. The other enhanced heat transportation to the north. Both demonstrate our main point. The slow rearrangement of continents continuously modifies climate by altering ocean currents. Earth's deep time is filled with these tipping points, moments when the position of plates rewired the planet's thermostat. Earth's climate has swung between two end-member states, icehouse and greenhouse. An icehouse climate describes cold, dry conditions dominated by ice sheets and glaciers. A greenhouse climate describes warm, humid conditions with little to no ice at the poles. Plate tectonics drives these shifts over millions of years. When continents move toward the poles, glaciers can form, reflecting sunlight and promoting cooling. When continents cluster near the equator, they trap heat and promote a greenhouse state. The Panama uplift contributed to an ice house trend by redirecting ocean currents and altering the distribution of heat. Doing this, it helped initiate the long-term cooling that defined the Quaternary ice ages. But plate motion can also cause short-term effects. When volcanoes erupt along plate boundaries, they inject ash and sulfur dioxide into the atmosphere, and these particles reflect sunlight, temporarily cooling Earth's surface, another form of tectonic climate feedback. Together, these processes illustrate the changes in the lithosphere cascade into the hydrosphere, atmosphere, and cryosphere, meaning when one system shifts, the others respond. Now let's go deeper in time, to about 1.1 billion years ago, when the supercontinent Rodinia stretched from the South Pole all the way to the equator. This configuration caused a chain reaction that may have frozen nearly the entire planet, a scenario called snowball Earth. When Rodinia covered such a wide range of latitudes, ocean circulation was disrupted, reducing heat transfer from the tropics to the poles. Ice, therefore, began to spread. And as reflective ice cover increased, Earth's surface absorbed less sunlight, and cooling accelerated until even the equator may have been covered in ice, as cold as modern-day Antarctica. This event shows the extreme end of tectonic influence on climate. By altering the shape and position of continents, plate motion can plunge Earth into a deep freeze, or thaw it again as continents drift apart. Now, link this concept back to Panama. While the uplift of the isthmus didn't freeze the planet solid, it did contribute to a measurable cooling event. Both cases demonstrate that small shifts in plate configuration can have enormous consequences for Earth's systems. And as we conclude, let's summarize how plate tectonics serve as the ultimate Earth sculptor, a force that continuously reshapes our planet's surface, climate, and life. We can identify three major system connections: evolution, continental separation and then reconnection isolate or merge species, which drives biodiversity. Ocean currents, opening and closing straits changes circulation, redistributing heat, fresh water, as well as nutrients. Climate. These circulation changes oscillate Earth between icehouse and greenhouse conditions over geologic time, and the Panama uplift embodies all three. It changed circulation, shifted climate patterns, and spurred evolutionary migrations that still shape ecosystems today. At this point, you should be able to generate a full and appropriate response to today's essential question: how have plate tectonics influenced evolution, ocean currents, and global climate?